Thank you, Paola. Good evening, ladies and gentlemen. Live from the University of Basel in Switzerland. The worldwide webcast is here as a guest of the National Center of Competence in Research on Nanoscale Science. And I welcome here on the floor Professor Günther Roth, Director of this Competence Center on Nanoscale Science. Professor Günther Roth, everybody read about the keyword nanotechnology in the newspapers. Nanotechnology, the technology of tiny objects, is already subject of novels and movies. It is said to be the technology of the future. What is your estimation?
I think for the term nanotechnology, it's too early. We still work in the field of nanoscience. Here we deal with objects, processes and properties on the length scale of few nanometers. 1 nanometer is the millionth of a millimeter. The objects we are investigating are single atoms, molecules, or even artificial atoms.
How about Albert Einstein? Is there any relation between your work and the work of Einstein?
For sure. In fact, the famous paper of Einstein on the Brownian motion is taken as a proof for the existence of atoms and molecules. And nowadays, with the scanning probe microscopes, we have the possibility really to image the atoms in real space.
Next year, Nanoscience celebrates its 25th birthday. With the invention of the scanning tunneling microscope in 1981, the nano world became accessible for the first time. What is the clue of this new special microscope?
If we hear a microscope, we think in terms of a light microscope. And this can only achieve 500 nanometers resolution. But now there are new microscopes, for instance, the scanning tunneling microscope. It's shown here where a tip moves across the surface of a silicon model, and a very sharp tip really senses atom by atom. The path of the tip is then recorded on a computer. Scanning the surface line by line gives us a three-dimensional image of the atomic surface.
We here see a picture of single atoms, and we just know that these are tiny objects. Can you give us a hint how tiny they are? How could we imagine the size of your atoms?
If you would enlarge a single atom of the size of an apple, you have to magnify the apple of the size of the globe. This means in terms of our scanning tunneling microscope, if we magnify an atom to a ping pong ball, the tip would have the magnitude of the Matterhorn. This is one of the reasons why it was discovered in Switzerland.
What are the actual research projects in nanoscience? What further developments have been made in the last 25 years?
As far as scanning probe microscopy is considered, it's mainly other interactions are taken into account. For instance, forces. There is the atomic force microscope. And even by using a tiny cantilever, you can probe the atoms on silicon surface, shown in the next slide. No, we hope, yeah, here. You can see the atoms made by atomic force microscope or scanning force microscope. But there are several main topics in our center, and they will follow now.
And now we see a short movie on the 5 main modules in the NCCR Nanoscale Science.
Was ist jetzt? Müssen wir das bringen?
Yeah.
No, hit the mute, sorry.
I'm sorry. Okay. So we hope that the movie is coming. I'm asking the techniques. Everything all right?
Kann die schauen das? No, now it's coming, no? Yeah.
With the invention of scanning probe microscopy in 1981, the nature of tiny objects, the world of atoms and molecules, became accessible for natural scientists.
Okay.
Basic processes of life take place on a molecular scale. Important applications of nanoscience lie in the field of medicine. Conventional blood analysis, performed by a chain of biochemical processes, often take more than 24 hours to be accomplished. Nanoscience
1, 2, 3, 4. Test.
To reduce this time to just a few seconds.
We have taken atomic force microscopy beyond imaging and developed a new kind of sensor that is based in nanomechanics that has a wide range of application in bioanalysis and diagnostics.
Tiny cantilevers that are functionalized to be attractive for special molecules bend whenever the molecules in question bind to the cantilever. Another research project deals with the development of tiny containers encapsulating single molecules.
A possible application of nanocontainers is in the field of the controlled and targeted delivery of drugs, where one makes use of the ability of the nanocontainers to interact in a controlled way with cells and proteins, which allows to transport them inside an organism to a predefined location where then the drug is liberated in a controlled way.
This technique could decrease the required dose rate by a factor of 1,000 or even more. By means of nuclear magnetic resonance, medical doctors produce three-dimensional pictures of the body with a resolution of about 1 micron. At the moment, 1,000 billion simultaneous spin flips are needed to get a measurable signal.
Compared to magnetic resonance imaging as it's used at hospitals, we improve the quality or the resolution by 15 orders of magnitude. So at present, it's still a research project, which means we cannot yet use it in an industrial environment. However, we can do the experiments at low temperature and ultra high vacuum, where we can measure very small numbers, something like 10 spins or even single spins.
Miniaturization of electronic devices has reached the length scales of only a few nanometers. In the near future, currents will flow through circuits that are only 1 molecule in diameter.
We start with a notched gold wire, which we stretch. And here we have a simple model. You see when we pull on this, there will be a gap will form. And this is done actually on a more gentle way on the atomic scale, for which we have this model here. If this gap has formed, we are able to fine-tune it by bending the substrate. And if the gap has the right dimension, the molecule will fit in between, as shown here. This is a molecule which, if fits into the gap, it will bind to the both sides, and then we can apply a voltage and a current flows.
Single molecules may also be used to store huge amounts of data within tiny structures.
This is a little bit like in checker games, where we have a checkerboard, like the lines that I'm drawing here, and the position of the actual checkers on the board stores the information of the state of the plane.
So in our latest experiments, we were able to construct such structures like a checkerboard, and by this, the data storage would be about 1,000 times higher than what we can buy nowadays.
In the field of quantum computing, the complex interaction between tiny objects is used to compute complex problems in a very short time.
The centerpiece of that proposal, which one can call a quantum transistor, consists of an artificial hydrogen molecule. This hydrogen molecule has binding forces, and the idea is actually to control these binding forces with electrical gates and thereby control then in particular the interaction between the spins in that artificial hydrogen molecule. And this is a very challenging, a very difficult problem. By now, many groups worldwide have catched on this proposal, and there are more than 10 groups around the globe trying now to implement this kind of artificial hydrogen molecule, this quantum transistor. And at this stage, we can actually say that the progress is very impressive, and we are basically close now to have shown most of the desired properties of such an artificial hydrogen molecule.
25 years after the invention of scanning probe microscopy, the world of molecules and atoms keeps most of its secrets. This confirms Richard Feynman's statement, which postulated in 1959, "There is plenty of room at the bottom."
This short overview gave us quite an insight into the upcoming technologies. At the same time, we saw that there will be need of highly specialized researchers. How do you educate the next generation to be prepared for these tasks?
He created at the University of Basel a new nanoscience curriculum. This means we have courses for bachelor and masters in this new field, and we have very many excited students, and it's a very successful course.
The first students in nanoscience got their bachelor a few months ago. One of them is Frank Zoller. Hi Frank. Thank you for coming to the worldwide webcast Beyond Einstein. You are among the first around the world to obtain a bachelor degree in nanoscience. Looking back, what are your experiences?
It has been very interesting, but also challenging. On the nanoscale, the borders between physics, chemistry, and biology are rather fuzzy. Nanosciences are very interdisciplinary. Our curriculum contains elements of all three topics, and therefore it's rather demanding.
Maybe it would have been easier to study either chemistry or physics or biology.
What is so exciting the nanoscience study is this interdisciplinarity. So for me, it's much more interesting to study nano than one of the classic fields.
If Einstein would be a young man nowadays, would he decide to study nanoscience rather than physics? What do you think?
As far as I know, Einstein did not really like the experimental work. And since this is such an important part of our curriculum, I think that Einstein nowadays would still study theoretical physics and maybe make some contribution to the development of quantum computing.
Frank, thank you very much for joining us in this webcast. We wish you all the best for your master's degree. Thank you. Professor Günterroth, what do you think will be the tasks of Frank and his colleagues in the upcoming decade? What are your visions for the near future of nanoscience?
I think they will have a very interesting future. They can work in the field of molecular electronics, nanomedicine, life sciences, or even more application-oriented fields of self-cleaning textile structures and so on. I think the next 25 years will be as exciting as the last 25 years in the field of nanoscale science.
Professor Günterroth, thank you for joining us in the worldwide webcast Beyond Einstein. We come to the end of this nano section. I would like to thank everybody who contributed in the production and the techniques of this webcast, and I give back to CERN in Geneva.